Hello everybody and welcome back to our Automata and Formal Languages class, and this is the Unit 3 of the class. In the first two units we covered some basic grounds in mathematical definitions and some overview of a few mathematical proof techniques that will be helpful to us throughout this class. And now we are ready to formulate our view of the theory of computation and start looking at very important questions when it comes to computing. One of the important questions in computing is, or in theory of computation, is effectively the question of what is a computer. It may sound like a silly question, because at this point in time, especially with the advances in the technologies, digital electronics technologies, we have computers all over the place. And but when we look at the foundations of these questions, what we would be interested in is to look at an idealized model of computation, or an idealized computer, which we call a computational model, and then try to analyze this computational model, and through this analysis we will be able to effectively recognize their power as well as their limitations. By recognizing their powers, we'll be able to have mathematical theories that will help us develop these models into real-life objects, such as the computers that we have nowadays. And with understanding of their limitations, in a foundation level, at a foundation level, we will be able to look for alternative models of computing. By understanding what is the limitations of the models we have, we will be able to uncover additional strategies to overcome the problems. So when we look at this question of idealized computers, we will basically look at several different kinds of computational models that are at our disposal, from the simplest ones that we will discuss now in the next couple of units, called finite state machines or finite automata, to more complex models, such as pushdown automata as well as the Turing machines. And these will basically help us understand what is at the core of the kinds of computations that each of these models are capable of doing. Finite automata are actually good models for computers that have a very limited amount of memory. And it might be surprising that what can be done with such limited amount of memory. But there's actually a lot of things that you can do with even the slightest amount of memory that you can think of, meaning just 1 byte. So 1 bit actually. A lot. Actually, we work with a lot of these finite automata or finite state machines a lot, in even our daily interactions, such as an automatic door opener, which we'll see in a few seconds, how it works and how it's formulated. A lot of the appliances that you work at your home are built on these kinds of models, and so these are actually very useful models of computation to look at, especially because these models are extremely simple to formulate and formally define, and analyze their powers very, very easily, as we will see in the next few units. So let's see the example that I was just talking about, an automatic door opener. So how will it look, an automatic door opener? It effectively is basically an actuator that, here we call it the door, and 2 sensors, a front pad and a rear pad. And these sensors could be either weight sensors, or ultrasonic rangefinder sensors that detect distances and so forth. So computationally, we can we can actually implement these things relatively easily with electronics sensing devices and motors. So as you see, the system is extremely simple, and the way that it operates is that it's either in it's in one of these two states, in a closed state or in an open state, and these states correspond to how or what's the state of the door. Is the door closed or is the door open? In fact, what this machine that I'm thinking about recognizes is, or thinks of the door being, is that the door actually is not a sliding door. It basically is an elbow door, so it opens up towards the rear pad, and that dictates the operation of the machine, and I will discuss this in a little bit. So the way that this machine actually works is that it will basically process 4 different kinds of inputs, and as you can see, since these rear pad and front pad are kind of binary sensors, basically there either is something at the front door or isn't. So this is a binary sensing thing, so it could sense 0 and 1, the presence or lack of the presence of anyone at the front door, and same with the rear door. So you have either a person at the rear door or an object at the rear door, or at the rear pad, or don't. So as a byproduct of this machine will be able to process 4 different signals, 4 different inputs. So the inputs of my machines are 4 things. It's either someone at the front door and no one at the back door, someone on the rear door and no one on the front door, someone at the rear door and someone at the front door, and no one either at the rear door or the front door. So these are the 4 different inputs that this machine will be able to process, and also as I said, it can control the state of the door as being in one of these 2 states, either closed or open. So depending on which state we are in, we can actually model the transition that this machine goes through and effectively model its means of computation with this state diagram that I'm showing here. So this diagram that, and we will encounter these diagrams a lot in this class, these we call them either transition diagrams or state diagrams, and interchangeably. So we'll have either transition diagrams or state diagrams, we call these. And the way that it works is that if the machine is in the state closed, meaning that the door is closed, the door remains closed if nobody's at the door, or somebody is at the rear door, or somebody is at the rear door and the front door. The reason that we stay closed in those cases is that if somebody is at the rear door and somebody appears in the front door, if we open the door, we might knock the person at the rear door down. So that's what I said, that the condition of this state being, or the door being controlled and being not being a sliding door, dictates that we will have to keep it closed, so this is because it's not a sliding door. So for safety, we keep it closed when somebody is at the back of the rear pad. Now, if the machine is at the state closed, meaning that nobody's or the door is closed, if somebody appears on the front door, then it transitions from the state closed to the state open, therefore opens the door, and it remains in the open state. It keeps the door open as long as somebody's on the front door. So if the person who had came to the front door, if they stay at the front door, we keep the door open. If while that person is in the front door, somebody appears at the rear door, we keep the door also open. And also, while the door is open, if somebody appears at the rear door, we keep the door open so that they can exit. So, and also because the door is already open, there is not the possibility of knocking them over. And then the door closes, or the state transitions from, the machine transitions from state open to state closed when nobody's present, either at the back pad or at the front pad. So this way we will be able to recognize that the people who have been at the door have exited or entered the supermarket, and then we'll close the doors. So as I said, we can represent the state of our system and the computation of our model visually, or our automata visually, with the state diagram. So this is our state diagram. Or we could represent it with a transition table. Both of these models represent the exact same thing, and later on, when we formalize these, we'll see that more formally, we will actually use the transition tables as a means of looking at and representing our computation. So the transition table, in this particular case, it actually is a two-dimensional case, meaning that it takes two arguments as input and produces one argument as output. So if you remember, when we talked about cross products, when you want to group up arguments of your function, you use cross products of the sets where these objects come from as the domain of your function, and then the range of your function will be the outputs, which usually is one object. So the domain of my function, so if I have my machine here, the computation of this machine comes from a domain that's the cross product of two things, and then it produces the result as an output. So you have two sets that you draw your argument, your inputs of this machine from, and each of these combinations of these inputs would produce an output. Now here, the domain comes from the domain of state of your machine, and then the input. And then the resulting factor is a state. Basically, if the door is open, remain open, or keep it closed. If the door is closed, open it or keep it closed. So my state are the rows of this diagram, of this table, and the input is the columns. So by looking at this, if you are in the state closed, you remain closed for the input neither, both, or rear. So if you're closed, you stay closed for neither, rear, or both. Actually, this should be rear. And then then you open it when somebody is at the front. Then if it is open, you remain open if the person is still in the front, or somebody else appears on the front, or somebody appears at the rear, or somebody appears, or people appear at both ends of the door. And then you close the door or you go to the state closed when neither persons or neither pads are producing any readings. And so as you can see here, then this machine can process a sequence of objects. It could start in a closed state, and then somebody appears in the front door, then it opens, and then somebody appears in the meantime in the rear door, then it remains open, then people exit and enter the department store or grocery store, whatever this example was about. You close the door, and so you go from state closed to state open, back to state closed, remaining closed, go to open, remaining open, and go to close, depending on which of the inputs that you see. One of the things to notice here is that this machine has a full representation and description of exactly what needs to happen on every single state and every single input at that state. We have 4 inputs, we have 2 states, the cross product is 8 elements long, and so as you see, for every single one of those 8 elements, we have something to do. This later on, when we formulate our machine, we give it a special name. It's called the deterministic finite automata, or DFA. It's because for every single option that is there in terms of the combination of its states and inputs, there is an action to do. So there's nothing that the machine guesses or that it doesn't know what to do. And there's no branching in here, so to speak. There are a lot of devices, as you can now see from this example, that actually fit into a nice example of a finite state machine or finite automata. An elevator controller, for example, is one. Its states represent, for example, the floor that you want to go, and the inputs would be the buttons that you press in the reading pad. So, for example, although this particular door opening example required 1 bit to represent its state and 2 bits to represent its inputs, the elevator example would require a little bit more bits, so several bits to keep track of the information that it requires to work with. But as you see, several bits, even a few kilobytes, it's still considered an example of limited memory. Another limit that this state machine has is that, in fact, it has no memory of its past. So it knows its current state, and it knows the next state to go depending on where it is and what it reads. It will not know what state it was 3 readings ago. So this is another example, another property of this machine so far. So this is what we call limited memory and representation of them as finite state machines. Finite automata and their probabilistic counterparts, which are called the Markov chains, are actually extremely useful tools when you're attempting to recognize patterns in the data. Sometimes the patterns are deterministic, so we use finite state machines. Sometimes your patterns are non-deterministic, and by this I don't mean non-deterministic in the sense of later we make a representation of non-deterministic finite automata, but rather probabilistic or stochastic. A perfect example of it is speech recognition. Speech recognition is a process by which your computer or your computational model reads the input that is the sequences that it's getting as sound waves, and then recognizes what was said depending on how different transitions pair together to represent different kinds of phonetics of a part of speech. And these things, which are basically called Markov chains or Markov models, have been used particularly in these examples. Another example is the examples of artificial intelligence, effectively pattern recognition techniques in computer vision that enabled your cameras to recognize faces and so forth, rely on these kinds of probabilistic state machines or Markov chains, and also keeping track of financial markets and predict changes in the financial markets is another example, great example of how and where actually these kinds of finite automata are effectively used. So now we're going to have to take a closer look at the finite automata from a mathematical perspective. We will develop a precise notation and definition of a finite automata and all of the terminologies that we need for describing and manipulating these finite automata. And then we look at the theoretical results that describe their powers and their limitations. Besides looking and getting a better and clearer understanding of what a finite automata is and what they can do and cannot, we will be able to also develop practices and kind of experiences that will make us comfortable with the mathematical definitions that we use, look at certain kinds of theorems and proofs that we need, especially in this relatively simple setting, which is finite automata. Alright, in the beginning, to describe the mathematical theory of finite automata, we will basically do this in the abstract, without any reference to a particular application or a particular computing machine. So to do that, we will first start looking at our finite automata as state machines, or as what we call a state diagram, as I said earlier. And state diagrams basically show us how many states our machine will have, which is the state in which the machine starts, we call it a start state, and what will be its accept state, and we'll talk about these later, and how states transition between one another, or rather how would the controller of our finite automata transition between states. Now, to do that, we're going to start with an example of a finite automata. And let's call this finite automata M sub 1. Let's suppose that this finite automata has 3 states. And we call these states Q sub 1, Q sub 2, and Q sub 3. Then the transitions will work something like this. So if the state is in Q sub 1, it stays in Q sub 1 if the input was 0. Then let's say that this goes to Q sub 2 from Q sub 1 if it read 1. Then it stays in Q sub 2 if it keeps reading 1s. And as soon as it read a 0, it transitions to Q sub 2. To Q sub 3. So upon reading a 0, it's going to Q sub 3. And then it transitions back to Q sub 2 upon reading either 0 or 1. Now this diagram should give me everything I want, because so this diagram should give me everything I want. It's so far, and we'll see a little bit later a couple of things that's missing. So I have the set of the states that I represent them with these circles. The input is going to be 0 or 1, and these arrows will tell me how my machine transitioned from one state to another when it receives a number 0 or input 1. Notice that each state has 2 outgoing transitions, 1 per input, and in this case I assume that my state the inputs are only 0 and 1, and then the state number Q sub 3 transitions, it has only 1 arrow pointing out, but that arrow is labeled with 0, 1, which means that it still has 2 arrows pointing out. I just combined those 2 arrows pointing out together to simplify the look of my machine. I represent the input state of my finite automata with an arrow that points to it from nowhere. This makes Q sub 1 be the input state. So basically what happens is that this indicates that the machine, when I just turn it on, it is going to start in Q sub 1. The accept state, which is also an important state to consider, we represent that with a double arrow. So any state that or a double circle. So any state that has 2 circles, that means that it is an accept state, and we'll see what these are: the input state and the accept state, and what is their importance in the definition of the computation of these systems. So the state that basically has an arrow pointing to it that comes from nowhere, this is going to be my start state. And a state with double arrows is going to be called an accept state. and then the arrows themselves will be transitions. So let's take a look and see what this automaton does. When this automaton receives an input, let's say 1101, it processes that input one at a time, and then it produces an output. So the automata takes a sequence of values as input. So its input is a sequence. We also sometimes call these strings. And then the output is going to be either accept or reject. Is going to be the output of my automaton. So the automata reads each input symbol from the input string, and then uses its transition to go from one state to another, and then it performs this over and over and over again until finally it reaches the end of the string. It's the end of the input. At this point, it produces an output. If by reading at the end of the string, if it was in an accept state, then it accepts it, and then it rejects otherwise. It rejects the string. So we call the processing of this finite automaton, or the computation that this finite automaton does, is going over the input string, going over every single input and transitioning according to its transition table. And when it is at the end of the input string, it decides to accept or to reject that string, depending on where it ends up. If it finishes, if once the string is finished, it is at an accept state, then it accepts the string. If it's not at an accept state, then we say that that string is rejected. So basically, this automata will produces a yes/no output. So for example, let's take a look at this string 100100. So when we read, let me actually redraw this automata down here. Okay, and now let's see what it does over reading the string. So let's say that my input was 1101. Okay, so we start from left. So we start in state q sub 0 or q sub 1. We read 1, and then according to this transition, I'm going to have to go to state q sub 2. So I go to q sub 2. Then I read another 1. Then according to my transition, I'm going to stay in q sub 2. So I see a 1, I go to q sub 2. I see another 1, I stay in q sub 2. Then I read a 0. When I read a 0, then I go to state q sub 3. And in state q sub 3, I read a 1. So 1 transitions me back into q sub 2. And as a result, then I'm going to accept, because I ended in Q sub 2, which is an accept state. So my machine accepts the string 1101 because it starts in Q sub 1, it goes through the string, and when it reads the last symbol and processes that last symbol, remember, it needs to process the last symbol. When it processes that last symbol, which is 1, then it produces the output that is Q sub 2, therefore accept this string. Let's take a look at this other example. Let's take a look at the input being 0, 1, 0, 1, 0, 0. Yeah, this is good. Actually, let's add 2 more zeros to it. And so let's take a look at this input. So this starts from, again, we start from Q sub 1. We read a 0. So the first 0 keeps us in Q sub 1. So when we read that, we stay in Q sub 1. Actually, just draw these a little bit more further apart. So I'll have space to show you the transitions here. So 0, 1, 0, 1, 0, 0, 0, 0. So I read the first 0, I stay in Q sub 1, then I read a 1, therefore I go to Q sub 2, then I read a 0, goes to Q sub 3, then it reads a 1 in Q sub 3, reading a 1, goes back to Q sub 2, reads a 0 from Q sub 2, goes to Q sub 3, reads a 0 from Q sub 3, goes to Q sub 2, reads a 0 from Q sub 2, goes to Q sub 3, and reads another 0, and then goes to Q sub 2. So this machine again ends up in Q sub 2, which is an accept state, so it accepts that string as well. Now let's look at this. So we call this input 1, input 2, and input 3. So let's take a look at now this input and see what happens with this input. What if we see something like this? 1, 0, 1, actually a little bit more space, 1, 0, 1, 0, 0, 0. Let's see what happens with this string. So your machine starts in Q sub 1, which is the start state. Then it reads a 1. When you read a 1, you go to Q sub 2. Then it reads a 0. When it reads a 0, then it goes to Q sub 3. Then in Q sub 3, it reads a 1, goes back to Q sub 2. Then it reads a 0, which takes it to Q sub 3. Then it reads another 0, which takes it back to Q sub 2. Then it reads another 0, which takes it to Q sub 3. And therefore, it rejects that string. So as we go through these strings, we'll notice that my machine accepted this string that ended with a 0, 1. Also, it accepted a string that had a 0, 1, and then it was followed by an even number of zeros. But it did reject this string that had an odd number of zeros after its last one. So this will be an interesting and nice question for you to challenge yourself, and the question to ask yourself, to go through this example of this finite state machine and decide what kind of language or what kind of strings are there that this machine accepts. Just a hint, if you look at all the transitions that have label 1 on them, they all go to Q sub 2. So one of the things that we're sure for by just immediately looking at this machine is that any string that ends with a 1, it is going to be accepted by this machine. What are the other strings that this machine accepts? And then you just think about it yourselves for a little bit. And as we go on, then we'll explain this machine a little bit, this state diagram and the machine a little bit more, and then we'll see what other kinds of strings, or what is actually the language that this machine accepts.